Hi, my name is Sarah Beth Seabury, and I'm going to talk about our recent paper where we look into the details of how fluid-induced earthquakes occur using a large-scale laboratory fault. So we conducted laboratory experiments on a 3-meter biaxial apparatus that creates slip events that are kind of similar to a natural fault. The sample has an injection well drilled so that we can inject water directly onto the center of the fault. We load up average normal stress. We can vary the level of shear stress, and then we can inject water directly onto the fault. So our experiments investigated how the initiation and the overall size of the earthquakes was different when the fluid was pumped in when the shear stress was really high. So the sample average shear stress is close to tau peak versus slightly above residual versus below residual. We found that in the near critical case, the earthquake occurred quickly and suddenly, and that it was able to rupture the entire fault, as seen down here. In the low stress case, we found that it took hundreds of seconds for the event to occur, and that the event did not rupture the entire fault. It was smaller and it ruptured a smaller portion of the fault. Using measurements from displacement, strain gauges, and a model of the fluid pressure, high stress case, when the fault was near critically stressed, the fluid pressure was required to start the earthquake, but then the event was sustained by energy already present in the rock rather than energy that was put in due to fluid pressure. When the fault was not near critically stressed, such as the slow case over here, we found that the earthquakes could only initiate after the fluid pressure had caused silent slip, so slip is in the red, to redistribute significant amounts of shear stress, as shown in the green. So we have this region of high shear stress that was caused by aseismic slip. And when that shear stress got high enough and the patch was large enough, then an event could initiate dynamic rupture. However, it's limited to the extent of the fluid pressure and the redistributed aseismic slip, whereas in the other two cases, the rupture only required a small amount of change in shear stress and then was able to rupture the entire length of the fault. And this is also pretty exciting because our experiments agree with recently published computer simulations that can illustrate how induced seismicity is strongly affected by the level of pre-existing stress within the rock. I encourage you to look up the paper to see more details. Thank you.